In the previous lecture, we studied the floating point representation that is the standard by the IEEE. In this lecture, we'll learn about floating point arithmetic. As usual, we're going to start with something that we already know. We already know the floating point arithmetics for decimal numbers, or at least we can recall how to do that right now. So if I have to perform the addition of those two numbers that are on the screen, 9.999 base 10 times 10 to the 1 plus 1.610 base 10 times 10 to the minus 1. The first step that I need to do is to align the decimal points so that the exponents of the base 10 expression are the same, because I can only add two numbers that have the same exponent. And the way I do the alignment of the exponent is by changing the decimal period in the number that has the lowest digit, the lowest exponent. So I always look at the value of the exponent. The number that has the lowest exponent is the one that has to be adjusted, assuming that the numbers are normalized like this. So I'm going to adjust this exponent to become 1. And because I make this exponent 1, I need to move the decimal point to the left by 2 positions. So the decimal point used to be here. It moved to the left by 2 positions to change it to 10 to the minus 1, 10 to the 1. Next, I can add the significance. So now I can add those two numbers and I get 10.015 base 10 times 10 to the 1. And after doing that, I have to renormalize the result. To renormalize the result, I need to move this decimal point 1 position to the left, which means that I need to add 1 to the exponent. Whenever I move either the decimal or the binary point 1 position to the left, I add 1 to the exponent. And finally, I may have to round off the result to the representation that I want, or to the representation that is available in the case of a computer. In this case, let's suppose that I wanted to have only 3 positions after the decimal point. So in this case, I will round this 1, 5 to 2. And we're going to look at the rules of rounding in a few slides. So for the floating point addition, let's say that I wanted to do this addition in binary. So I want to first convert those two numbers to the floating point binary representation, and then I want to perform the binary floating point addition of those two numbers. So first I want to compute the binary representation of 0.5, and 0.5 is 2 to the minus 1, which is 0.1, which is 1 times 2 to the minus 1. The difference between here and here is that I moved the decimal point 1 position to the right. Now that I moved the binary point. Now that I moved the binary point 1 position to the right, I needed to subtract 1 from the exponent. And to convert the number 0.4375, what I need to do is, what I can do is just to remember that 2 to the minus 1 is 0.5, 2 to the minus 2 is 0.25, 2 to the minus 3 is 0.125, and so on. So the same way that I remember the powers of 2 for the integers, I can remember some of the powers of 2 for the fractions. So I can express this 0.4375, and I can subtract then 0.25, that's the largest fraction with a negative exponent. So it's the largest of the fractions that I can fit into that number. And I get the remainder that is 0.1875. And then the next number that I can subtract from it is 0.125. When I subtract that number, I get 0.0625, which is already 2 to the minus 4. And so I have now computed the binary representation of that number, this time instead of using the method of the repeated multiplication, I use the method of the repeated subtraction. The difference from the integers is that the values that I'm subtracting now are the various powers of 2, but where the exponents are negatives because I'm working with fractions. So with that, I can express this number as 0.25 plus 0.125 plus 0.0625. And then I can express those as the corresponding powers of 2. So this is 2 to the minus 2 plus 2 to the minus 3 plus 2 to the minus 4. And I can represent this as 0.0111, remembering that this would be 2 to the 0. This would be 2 to the minus 1, 2 to the minus 2, 2 to the minus 3, 2 to the minus 4. Those are the corresponding positions. And now I can normalize the number. To normalize this number, I need to move the binary point 2 positions to the right. And that will give me, then I need to subtract 2 from the exponent. Having done that, I have the binary representation for the 2 numbers that I want to add. So which number should have its significant adjusted? And of course is the number with the smallest digit. So I'm going to represent this oh sorry, I should have moved my picture here. Let's do that right now. I apologize for that. I was looking at the slide instead of looking at the video. So now I wanted to do this subtraction. And to do the subtraction, then I will have to adjust the exponent so that the exponents are the same. The way I adjust the exponent of the 1.110 is by moving the binary point 1 position to the left, which implies that I need to add 1 to the exponent. So what I have now is 1.000 times 2 to the minus 1 minus 0.111 times 2 to the minus 1. And I can do the subtraction. What I will obtain with this subtraction is 0.001 times 2 to the minus 1. And then after I complete the subtraction, I need to renormalize the number. This renormalization will be moving the binary point 3 positions to the right. And whenever I move the binary point to the right, I need to subtract 1 from the exponent. So I have 1.0 times 2 to the minus 4, which will be 1 over 16. So that was the floating point addition. How do I do floating point multiplication? So in floating point, the multiplication is actually easier than the addition. So I can assume that we, in this example that we have in the slides, we're going to assume that we can only store 4 digits of the significant and 2 digits of the exponent in a decimal floating point representation. So we're going to start with decimal again. The idea of doing decimal first before doing binary is to always start with something that we already know. So the question here is, how would you multiply 1.110 in base 10 times 10 to the 10 by 9.200 base 10 times 10 to the minus 5? I putting those zeros to the right here to indicate that I always want to express the numbers with 4 digits. And when normalized with 4 digits, I'm going to have 3 digits to the right of the decimal point. The step 1 for multiplication is to add the exponent so that I can find what the new exponent of the number is. So I have the exponents 10 and minus 5. So 10 plus minus 5 is 5. And next, I multiply the significance. So I'm going to be doing this multiplication here. which will give me 10.212. So this is 10.102 times 10 to the 5. Now I have to normalize this number, and to normalize I need to move the decimal point one position to the right, which is corresponding to adding 1 to the exponent. So now I have 1.0212 times 10 to the 6. And the fourth step is to round off the product. So because I said in the beginning that I want to have only 4 digits, I need to round this off. And because this number is a 2, you always round it down. Any the numbers 0, 1, 2, 3, and 4 are always round down. The numbers 6, 7, 8, and 9 are always round up. We're going to discuss what happens with 5 later. Now, to do accurate arithmetic, assume that you can only store 3 significant decimal digits. So if you have 2.56 times 10 to the 0, and you want to add that to 2.34 times 10 to the 2 in decimal, what you'll have is that, and we are assuming here, and the most important point of this slide is that we have a limited number of places to keep our digits. So in this assumption, in this example, we only have 3 digits that we can have for the mantissa and 1 digit for the exponent. So I need to first, for an addition, I need to first adjust the exponent of the smaller exponent. The smaller exponent here is 0. When I adjust that to become 2, I need to shift the number to the right. And in this case, I end up losing the 5, 6 because I have no place to keep the 5, 6. So I perform my addition and I find out that the result is 2.36 times 10 to the 2. Now assume that you can also have room for a guard and for a round digit in this representation. So a guard and a round digit is a new concept that we are introducing right now. It's those are internal digits that the adder has in order to keep more information when aligning the exponents, so that those numbers that I would have lost, those digits that I would have lost, are not lost during the addition. I only do the adjustment to put it back into the representation that I have, in this case, the 3 digits, after I perform the operation. So this is a very important concept that we're going to be working a lot in the homeworks and in the exams and such. And the concept is that the round and the guard digits are internal to the adder. They do not exist outside of the adder. They do not exist in the registers of the machine. They only exist internally, and they are only used for us to be able to do more accurate arithmetic operations. So the idea here is that when I did my shift to the right for my 2.56 times 10 to the 0, so that I could adjust the exponent for the exponent become 2, before I had lost the 5, 6. Now I have 2 additional digits. One digit is my guard digit, the other is my round digit, and they can keep the numbers. When I do my addition, I do the addition including the guard and the round. So my the result of my addition now is 2.3656 times 10 to the 2. Now that I have completed my addition, I do not have room for the guard and the round in my registers. So in this decimal example, I only have room for 2 digits, but now I know that the digit that comes after the 6 is a 5, and then after I have a 6, so this is 56. 56 is bigger than 50. And therefore, I definitely should round up. And the result now, so remember I told you 0 to 40 round down. So 0 to 49 you round down, and 51 to 99 you round up. So this is 56, I should round up. And the other rule is that the number 50, if this was 50, then you'd round to the near, let me get my mouse here. So if this number here was 50, then you'd be rounding to the nearest even, which means that you do the round here to make this number become even. So if this was a 0, this would be a round down, which means that the 6 would remain because we favor the even numbers. The reason for this rule to favor the even numbers when we have 50 is so that we don't introduce a bias in a large collection of numbers. Because if we are to round 50 always up, in a large collection of numbers, in a large database, when you add all the numbers, would be introducing a bias that would make the result slightly larger than it actually is. So by always rounding to the nearest even, we're going to be rounding some of the numbers that are right in the middle up and some of the numbers that are right in the middle down. And assuming that there is an even distribution of even and odd numbers in a large collection of numbers, then this will average out when we do summarization of the results, for example, by adding them all up. Okay, so much about rounding. So this will be going to round up. Therefore, the result is 2.37, which is closer to the actual result than what I had before, that was the 2.36. So about rounding. Rounding becomes much more important in binary than it was in decimal. In decimal, if I consider 2 digits that for rounding, for example, if I want to round this to a number that has no decimal values to the right of the decimal period, I would have 100 different combinations of numbers with 2 digits to do the rounding. And I would have from 0 to 49, I would be rounding down. From 51 to 99, I would be rounding up. It's only the 50, that's 1 out of 100, that is a problem. Now, if you consider the binary situation, and I have only, I have, again, 2 digits, and I have only 4 combinations. And among those 4 combinations, if I have 0, 0, or 0, 1, I round down. If I have 1, 1, I round up. But there is the 0, 1, 0 is equivalent to 0.5, and that's the problematic rounding. So while in decimal I had 1 out of 100, that was a problematic rounding. In binary, I have 1 out of 4. So 25% of the time, I am in the middle. So rounding becomes a much more important consideration when we talk about binary numbers because of this equivalence. So to solve that and to make arithmetic in computers more precise, the designers of adders and of arithmetic operations have devised a new bit that is called the sticky bit. The sticky bit is very important to understand because the sticky bit gives me much more precision and needs to be used carefully. The idea of the sticky bit is that ideally I would like the intermediate computation that happens inside the adder to have infinite precision, which means that when I do the shift to adjust the exponents in order for the exponents to be the same, I would like ideally to keep all the digits that I need to shift. The problem is how I differentiate between 2 numbers. Let's say that a number is 0. In decimal 0.5 and has all zeros to the right of it, and a number that is 0.5 has many zeros and then a 1, or any other digit that's non-zero. So if the number that has 0.5 and then eventually has a digit that's non-zero to the right, it doesn't matter how far to the right, that number is bigger than 0.5. And the number that's 0.5 and then has all zeros to the right, that number is exactly 0.5 in the representation that I have. The solution is to use a bit that's called the sticky bit. The sticky bit is 1 whenever there is a non-zero to the right of the round bit. So remember that I'm doing the shift, I keep in the guard, I keep in the round, and I throwing away some other bits. If any of the bits that I'm throwing away is 1, no matter what the position, the stick bit becomes 1. So let's do this with an example with the stick bit, because I think it will become a little bit more clear what we are doing. And in this example, I want to add 5 decimal 01 times 10 to the minus 1 to 2.34 times 10 to the 2. And again, I'm doing decimal because we are used to decimal, and then of course we can repeat that in binary. So here is my mantissa for both numbers, 5.01 and 2.34, and my exponents minus 1 and 2. Of course, I'm going to be adjusting the exponent of the number with the smaller exponent. That's what I always do in addition. So I'll be adjusting the number 0.501. Sorry, the number 5.01. And what I do without the stick bit, so this is the example with no stick bit, I lose this one here. This one is gone because I don't have any room to put it. I have occupied all the bits that I have in my adder. I kept the guard, I kept the round. And now the exponents are the same. I can do the addition, and the result of the addition will be 2.34, and then there will be a 50 in the garden round. And then I'll do my rounding now. Because this is a 50 and I have no more information, I have to assume that this is exactly 50. Then the rule is that I should round to the nearest even. This number is already even, so I round down, the number remains, and the result is 2.34. Now, if I repeat the same operation with the stick bit, I have one additional bit here. I know that in this example, it looks like that this one just moved into the stick bit. That's not exactly what happened. This one could be much farther to the right, and it could be a different digit. No matter what that is, this sticky bit would go to 1. So now that I do the operation the stick bit, I consider the value of the stick bit in the end. So, and when I do the add of the stick bit, it's slightly different than the add of all the other digits. With the stick bit, you consider that to be just an OR function. So if either one of the stick bits or the operands is 1, the stick bit is 1. But let's say that I end up with a situation where both stick bits are 1 because I'm doing a series of operations. If that were ever to happen, you don't have a carry. There is no carry from the stick bit, because the stick bit is just recording whether there is any number to the right that is not 0. And you don't know where those numbers are. They are just to the right somewhere. So just be careful with that. It's very seldom that you have a situation in the exercise and such where you have 2 stick bits that are equal 1. But internally in a processor, you may have 2 stick bits equal 1. And if they ever happen, the result is that the stick bit is 1, but there is no carry. So with the stick bit now, the 50 has to be rounded up, because this is not 50 actually, this is bigger than 50. And a number that's bigger than 50 ends up being rounded up. And the result is the more precise result, 2.35. So the IEEE standard 754 specifies additional rounding control. There is this extra bit for guard, round, and the sticky bit. So the sticky bit is part of the standard, and anybody that implements the standard must implement the sticky bit. There are choices of rounding modes in the standard, and the standard allows the programmer to fine-tune numerical behavior of the computation. Not all floating point implementation now all implementations of the standard implement all the options that are in the standard. Most programming languages and floating point libraries just use the defaults in the standard. And there is a trade-off between hardware complexity, performance, and market requirements that must be followed when you are designing such a unit. So There are many. If you start googling for floating point errors in common news outlets, you're gonna find that over the years there have been many floating point errors that made the news, and it's not a good thing for a company to have its floating point unit in the news, because usually it's very bad news. So, for example, there is this very interesting story about the Vancouver Stock Exchange rounding error. This was in 1982. Someone wrote a program where instead of returning the round of a value, they returned the floor of a value. And the consequence is that there was a particular stock that started initially at 1,000 points, and after a number of some time operating, the stock was back. It was down to half of its value, and nobody could understand why, because it was not explained by what was going on in the market. And then when they went to investigate, they found out that someone had made the mistake in the program, and instead of using round, they were using the floor. This is just one example. If you look at the floating point errors for Intel, and there's a number of years ago that Intel had a problem with their floating point unit, and you look at the cost of replacing the chips for Intel, it was a huge loss for the company. So floating point corrections and floating point rounding errors are very important. In banks, usually the banks do not use floating point, and we're gonna see that there are certain numbers that cannot be represented precisely with floating point, especially 1/10, for example. So to be more precise, the banks use a decimal converted to binary notation instead of using floating point. So errors in floating point can be very important. And talking about errors in floating point, there is one more concept that we need to cover, that is the associativity of the floating point addition. Let's assume that I have a value of x that is minus 1.5 base 10 times 10 to the 38. And I have a number y that's 1.5 base 10 times 10 to the 38. And I have a third number that's the number 1. And let's say that I wanted to compute the addition of these three numbers, and of course addition is associative, right? You have known for all your life that addition is associative. So I should get the same result whether I compute I plus zeta and then I add the value of x, or whether I compute x plus y and then I add the value of zeta. So let's assume that I only have room to store 32 decimal digits for the significance of any of these numbers. So let's do the first computation. I compute y plus zeta and then I add x to it. So I computing 1.5 10 times 10 to the 38 plus 1, and then I will be adding the value of x to it. Well, the problem is that I only have 32 decimal digits that I can represent here. So when I adjust this number to have the same exponent as this number here, I get the number 0. Because that one got shifted 38 positions to the right, and I only can represent 32 positions. So because of the limit of how many digits I can store, the result of that addition is 1.5 base 10 times 10 to the 38, and when I add that with the number of x, I get the value 0. So adding minus 1.5 times 10 to the 38 with plus 1.5 times 10 to the 38 with 1, I got 0. And then of course, if I do the computation the other way around, where I first add x to y before I add to zeta, the two numbers will cancel because they are the same value with this different signs. So this will be 0 plus 1, and the result will be 1. So the problem that we have now is that when you have limited representation for your floating point numbers, addition is not associative anymore. So great care has to be taken into programming when you can run into a situation like this. So whenever you're doing a computation where you may be operating with numbers that are very have very different magnitude from each other, you may end up with situations like this, and you need to be very careful programming your floating point computation because addition is no longer associative. Parallel programs may interleave the operations in unexpected orders, and we have already seen the issues with synchronization. For example, when you're doing parallel programming, you may do synchronization through a lock, and who obtains a lock first is arbitrary, depends on the system. So your assumptions of associativity may fail when you have parallel programs. So here is an example, is the same example that we just did before. So we need to validate parallel programs under various degrees of parallelism and on various assumptions when we are using floating point. So there is this question about who cares about floating point accuracy. Well, they are very important. It's very important for scientific code, but do everyday consumers use floating point accuracy? Well, you wouldn't be happy if your bank balance is out by 0.002 cents, because if those errors would accumulate over time, it could make a huge difference, especially in bank accounts that have lots of traffic to them. So as I was telling you, to look up the Intel Pentium FDiv bug. And then you're going to see that there was a huge repercussion to the company, not only in terms of reputation, but also in terms of the accuracy, in terms of money. They lost lots of money because of that error. Finally, floating point in our instruction set architecture for RISC-V. The instruction set architecture supports arithmetics, it supports signed and unsigned integers. Floating point is an approximation of real numbers. There is a bounded range and precision for floating point operations. The operations can underflow or overflow. In RISC-V, there are 20 instructions that are the most popular instructions in floating point, and they account for 76% of all instructions executed, for example, in the spec CPU 2006. The floating point instructions account for 16.4% of those popular instructions. So that's what I had for floating point arithmetics.